Hello, Assalamu alaikum. How are you all?
Walaikum Assalam.
Is the slide visible to all of you?
Yes.
Okay. All right. So we will start off with the rate of reaction and chemical equilibrium. Um, I think we in the last session we started off with a bit of a gist of rate of reaction, right? Um, there are various factors which affect the rate of reaction. When we look into the chemical reactions, the rate of the particular chemical reaction can be um, looked into by how the products are formed or the amount of product which is formed per unit time. Okay. I told you that the rate of reaction is basically the rate of the speed of that particular reaction, where the reactants are going to react with each other over a certain period of time and the new products will be formed. So the mass of the product which is achieved and the reactant mass which is lost, okay, over that certain period of time, it is going to be the rate of that particular reaction. So to simply define it, it is basically the speed of the at which the reactants they form products, or you can also say the speed at which the reactants are lost to form new products. Okay. So you can see it both ways. And specifically, when you look into the investigation of how they are, how the rate of reaction is particularly investigated, you look into both ways. Okay. Then, when we look into its importance here, rate of reaction is this rate of reaction is basically um, has various factors where its significance lies. Okay. So industrial processes, we're going to look into that the rate of reaction is very crucial. For instance, particularly in your syllabus, you have a reverse process and the contact process whereby sulfur dioxide is produced from sulfur dioxide and oxygen. The controlling the reaction and optimization of different reactions. Okay. When we look into the different factors which affect the rate of reaction, we see that concentration, pressure, surface area, temperature, and catalyst. All of these primarily five major factors, they affect the rate of reaction. We say that concentration, last time I told you in the last section, I told you that concentration basically depends upon or is the number of moles of the solute over the volume of the solute. Okay. So, for instance, if I'm saying that I'm not changing the volume, but I'm increasing the concentration, the volume remains constant. This means that I am increasing the concentration, increasing the amount of the solute or the number of moles of the solute, which means that greater concentration is directly related to greater amount of moles. Okay. So decreased concentration would likewise means that the amount of moles have also decreased. Okay. So we can say that increasing the concentration in that similar space of volume. For instance, I say that you have two different reactants, they're both reacting with each other. Here you have less concentration, but in the next case scenario, you have greater concentration. You have not changed keeping the volume constant. You've simply increased the number of solute in that same volume, which means you are increasing the concentration. Obviously, if you're going to increase the concentration, the particles, there are greater number of particles in the same amount of volume, which will increase their frequency of collisions. When the frequency of the collisions with the neighboring molecules takes place, the rate of reaction tends to increase as well. Okay. So this is directly related to the rate of reaction. All right. When we talk going to talk about pressure, when we look into pressure, what happens? The greater the when you increase the pressure. For instance, in gaseous phase reactions. In gaseous phase reactions, what takes place? For instance, if you have the Haber process, nitrogen is reacting with oxygen, it is referred to as a gaseous phase reaction, where ammonia is produced. Okay. So when you increase the pressure, the rate of reaction tends to increase. Why is that so? Because increasing the pressure directly impacts the volume of the container and the gas. Okay. It is inversely related to the volume, which means increasing pressure would decrease the volume. When it decreases the volume of the gas and of the container, this allows the gas particles to come closer together. Okay. When the gas particles they come closer together, they are going to collide with each other more frequently, thereby increasing the rate of reaction. Are we clear so far? Yes. Any questions? All right. Moving on to the next one. If anybody has any questions and they don't feel convenient unmuting themselves, they can also type in the chat box. Okay. Surface area. Now, what is surface area? We see that surface area also tends to increase the rate of reaction. How? Now, all of these, when you're going to be answering all of these factors in the exam paper, you are going to refer to how each factor impacts the rate of reaction, but you will be asked in terms of particle collision theory. So, what is particle collision theory? That how these factors impact the collision of the particles first, hence, thereby increasing or decreasing or influencing the rate of a chemical reaction. Okay. So, for instance, we just saw and we looked into that concentration and pressure, they directly impact, they increase the frequency of the collisions, hence, which is why subsequently increasing the rate of reaction. Okay. Next, we see that, okay. Next, we see that increasing the surface area. What do we mean by increasing or decreasing the surface area? Can someone tell me? Yes, Abdul Basit.
Yes, we can increase surface area by turning the compound or element into the powder form.
Into powdered form. Yes. Powdered form basically means very good. Powdered form basically means that you're increasing the surface area. You are allowing, you get increasing the area of the particles to be colliding with that particular reactant. Okay. So the increase, for instance, if I say you have a marble chips and that is limestone, you have in chemical way you can say it is calcium carbonate. Okay, so you have CaCO3. That is in three different forms. For instance, you have it in lumps, bigger lumps, and in other ways you can say that you have smaller chunks, okay, or small pieces of it, right? And you also have powdered form. This means that powdered form has greater area. It allows the other reactant molecule to react with each other since it has greater area. They are very, very tiny granules, okay, or very small, they're so fine particles that which increase the area, they increase the surface area, thereby the rate of reaction tends to increase. Okay, more of the product would be formed in less amount of time. So increase in powder form has greater surface area, whereas lumps they have the least surface area. Okay. Temperature is that when you how do we link temperature with the rate of reaction? What is temperature going to do? Yes, Zoya.
Temperature causes the particles to gain more kinetic energy, so
Hmm.
they start moving faster and colliding more. So, because of these more collisions, it will react.
Yes, the rate of reaction is going to increase. Very good. So basically, temperature increases the average kinetic energy of the molecules. Okay. When it increases the average kinetic energy of the molecules, they tend to react faster. How? By colliding with each other greatly. Okay. Their number of collisions increases. We say that the frequency of the collisions tends to increase, which is why the rate of reaction is also going to increase. Next up, we have catalyst. Catalyst, they speed up the reaction. How do they facilitate the rate of reaction? The presence or the absence of the catalyst. This is what they are going to ask. So, for instance, if you don't have a catalyst, a particular rate of a particular product is formed at a particular time period. All right, for instance, I say that 50 is the amount of product which is formed, and till this time, which is t1. Okay, but for instance, if I add in another I add in a catalyst to this particular reaction, this reaction is going to, the rate of the reaction changes. It is going, the graph is going to look more steeper, and the same amount of product will be achieved in less time period. Okay, so if you look into this graph, you can see here that this will be your new time. Okay, this t2 is going to be the new time, which is for the second experiment. And we say that this blue line, which is the second experiment, shows or represents that the rate of reaction has increased. How? Because it has a steeper curve. The more the steep the curve is going to be, it means that it directly coincides or correlates to the rate of reaction. It directly corresponds to the rate of reaction. So the steeper the curve is going to be, this means that it has greater rate of reaction, and the same amount of product, you see that 50 grams of 50 is the amount of the product, it is formed within less time as compared to for the first graph. Okay, and the steepness basically tells you the it or is determined by the gradient of the curve. Okay, so actually, in other ways, you can also say that the gradient of the curve actually is going to determine the rate of the reaction, and this can be determined by the curve or the graphical representation by looking into the gradient of the curve. Okay, is this point clear so far?
Miss, I have a question.
Yes.
How exactly does the catalyst speed up the reaction?
Hmm. The catalyst, they speed up the reaction by allowing, let me just give you an example in this way. For instance, you have two different points. Okay, you have point A and you have point B, and this point B is your destination. You are present at point A. Okay, and this is a hill that you have to cross, and then you have to reach point B. All right, obviously this is going to be very time consuming because this is a long pathway, this is a long route. Okay, whereas if, for instance, you dig a tunnel, all right, and you go through this tunnel from A to B, this pathway is going to consume less amount of time. Okay, so this is how basically the catalysts, they tend to react. What do they do? They provide an alternative pathway for the reactants to react to produce their products by decreasing the activation energy of which is required by the reactants to produce the products. Are you getting my point? So this minimum activation energy, or the activation energy, which is the minimum amount of energy required by the reactants to produce their products, is the EA. which is the activation energy, right? So the catalysts, they actually decrease this activation energy. When the reactants, they don't need so much of that energy. So even if they possess a bit of amount of energy, they are going to only absorb some more amount of energy from their surroundings, and then they will be producing their products. So this is how catalysts tend to speed up the reaction. Are we clear?
Yes, miss.
Okay. Any further questions up till now? Any questions by far? Just give me a minute. All right, moving on to the next one. So I gave you a basic gist of it. Let's just go through all of the factors separately as well. So we said that increasing the concentration, the greater the concentration, this means the number of particles tends to increase. Concentration is directly related to the number of moles of the solute, keeping in mind and keeping in view that the volume remains the constant. So the collisions, they are going to increase. This means that greater number of collisions, they take place. As a result, the rate of reaction is also going to increase. So we can say that concentration and rate, they are also directly related to each other. Okay. If you increase the rate of concentration, the rate of reaction is also going to increase. If you decrease the rate of reaction, if you decrease the concentration, the rate of reaction is also going to decrease. Similarly, if you look into the effect of pressure comes into play when you have gaseous phase reactions, where the reactants and the products, they are in the gaseous state. So the higher the pressure, this means that more collisions take place. Why? Also, there's one more thing that you must look into here as well. That, for instance, if I say higher pressure either means that you're implying greater force, okay, over a certain volume. This means that you are increasing the pressure by decreasing the volume. Okay. So force is applied to a certain area by increasing the pressure. Also, this can be said in other ways, that if you have greater number of gaseous molecules, okay, greater number of gaseous molecules or gaseous particles, this increases the pressure as well. How? Because of greater amount of collisions or greater frequency of the collisions. The gaseous particles will be colliding with their neighboring molecules frequently. Also, they are going to collide with the walls of the container, here, thereby increasing the pressure. Okay. So effect of pressure is looked into when we're going to go through the Haber process, where you see that the nitrogen and hydrogen, both of them, they react with each other to form ammonia, in the manufacturing of ammonia. And also we're going to look into in the contact process. Okay. The next one is surface area.
Yes, I have a question.
Yes, Rayan.
For the previous slide, you said so when you decrease the volume of the gas, the pressure increases.
When we increase the pressure, the volume of the gas decreases.
So how
When
do you?
when we increase the pressure,
Yeah.
increasing pressure means that you are decreasing the volume. Okay, you are subsequently decreasing the volume of the gas and the container. For instance, if I say that you have a container, okay, and this is the plunger. All right, these are the gaseous particles. They're obviously, they have certain pressure, right, within this certain volume. But when you push this plunger down, you push this plunger inside, this means that you are decreasing the volume, thereby allowing these gaseous particles to come closer together. When they come close together, obviously, when you're decreasing the volume, this means that they have less space to move around, right? So, which means that you are allowing them to collide with each other more frequently. All right. So when the frequency of the collision increases, the rate of reaction increases. So we can also say that the pressure and the rate of reaction, they are directly related to each other. Increasing the pressure increases the rate of reaction, and decreasing the pressure would decrease the rate of reaction. Are we clear, Ryan?
Then how do you increase the pressure?
How do we increase the pressure? We increase the pressure by using the barometer. Like for instance, if I'm using it, all the reactions which basically take place, they specifically talking about the gaseous phase reactions. So you will be increasing the pressure by the pressure ball. Okay.
Okay.
You can keep the pressure to be 100 atmospheres, to be 200 atmospheres, to be 300 atmospheres. It completely depends upon you. And when you're increasing the pressure, the volume of the gases, they are going to decrease. Pressure and volume, they are inversely related to each other. Okay. All right. Then the next one is surface area. We have discussed surface area. Smaller pieces, they tend to react faster. We see here that there are solid, large reactants, and there are some powdered forms. So in fine powdered state, you see that there's so tiny granules that which basically increases the surface area, allows more of the other reactants to collide with this finely powdered state of substance. As a result, the rate of reaction tends to increase, and we discuss this limestone or the marble chips. That is your calcium carbonate. Okay. Next, we have the effect of temperature. Increasing the temperature means more kinetic energy, or more average kinetic energy of the molecules, allowing them to have greater frequency of collisions. As a result, the rate of reaction tends to increase. Okay. For instance, if I say that you are using a warm dilute sulfuric acid, and in the next one, and it reacts with a magnesium ribbon, and the other one, the magnesium ribbon is reacting with, or magnesium is simply reacting with your cold dilute hydrochloric acid. So the one which is warm dilute hydrochloric acid will have greater rate of reaction. So the hydrogen gas bubbles, which will be seen or observed as a part of the chemical reaction process, they will be produced at a greater rate. Okay, more hydrogen gas bubbles will be produced in less amount of time with warm dilute hydrochloric acid as compared to cool or cold hydrochloric acid. Okay. Next, you have the effect of catalyst. So here in this one, you can look into that the catalyst, they basically tend to decrease the activation energy. Decreasing activation energy means that the reactants now require they need now less amount of energy to be able to carry out this chemical reaction to form new products. Okay, so the reactants, the delta H or the enthalpy change does not at all change. The reactants and the products, they still have the same potential energies. Their relative energies, they still remain the same. However, the activation energy of the reaction decreases. Okay, for instance, if you look into this one, without the catalyst, the activation energy is this much. This means the reactants, they need this greater gap of activation energy, which is required by the reactants to produce the products. But as soon as you add in the catalyst, this has now decreased the activation energy. Okay, so activation energy is always from, in this reaction profile diagram or the energy profile diagram, you can see that from the reactants energy till the top hump, or till the transition state, this is your activation energy. So this blue line that I'm marking, this is basically the activation energy with the catalyst. Okay, which is way less as compared to in the absence of a catalyst. Okay, so we can say that catalysts tend to increase the rate of reaction by providing an alternative pathway, also lowering the or decreasing the activation energy, thereby increasing the rate of reaction. And one particular example is enzymes in biological reactions. Enzymes, they are biological catalysts. They tend to increase the rate of reaction, and in particularly in human body systems and all, right? Any other example where you see that enzymes, they react and increase the rate of reaction? Any other example other than human body systems? Yes, anybody? Nobody knows. Basit, Fahad, Ibrahim, Rayan, Shafe, Zoya, Ayla.
Miss, can you repeat the question?
Sorry, Basit, come again.
Repeat the question.
I'm asking, give me an example of enzymes where enzymes react in a chemical reaction to speed up the process. But it should be other than any human body systems. This is also a part of your syllabus.
Miss, can I say?
Yes, Zoya.
Catalase from hydrogen peroxide.
From hydrogen peroxide. No, I'm particularly talking about the enzymes,
Catalase.
biological catalysts, any biological catalyst.
Yeah, I said catalase, isn't that one?
Catalase, yes. Okay, and anybody else? Ayla said in the Haber process and the contact process. In the Haber process and the contact process, these are chemical reactions. Yes, Ryan.
Isn't there an enzyme called pectinase for fruit juice?
Hmm. Yes. Yes, very good. Also, there is the reaction that you will study in organic chemistry, where you see that carboxylic acid or ethanoic acid is produced by the oxidation of ethanol. And ethanol is produced by the fermentation of glucose. Okay. And that fermentation of glucose in a biological way, it requires yeast, and yeast has the catalyst, which is zymase. Okay. This zymase is basically your biological catalyst. Okay. So very good. Good. All right. Moving on to the next one. Okay. So how do we basically investigate the rate of reactions? There are various ways in which you can actually investigate the rate of reactions. How? You can either look into the how much of the product is produced. You can also over a certain period of time, and you can also look into how much is the reactant lost, okay, over the certain period of time. Both of these case scenarios, the change in the amount of loss of reactants and the change in the amount of product which is produced over that certain period of time, is going to be your rate of reaction. Okay, so investigating the rate of reaction, this is the these are the two different setups. If for instance, if you look into the first one, in the first one, the gas which is collected using a gas syringe system. Now the gas here is collected in a gas syringe. This means that they are looking into the product which is formed over a certain period of time, right? So for instance, the two reactants, they react with each other. For example, this reaction, it can be looked into that magnesium reacts with hydrochloric acid. Now, you know that when metals, they react with acids, what do they form? They're going to form a salt. That is going to be magnesium chloride in here in this case scenario. Why? Because the metal has to replace or it has to displace hydrogen from its acid to produce the salt, and hydrogen gas will be released. This hydrogen gas, which is released as a result, or any other reaction you can take calcium carbonate, metal carbonate reacting with acids, okay, magnesium carbonate reacting with acids. So in this particular reaction, when the carbon dioxide gas or any other gas which is evolved as a result, it is going to go through this delivery tube, and as it goes through this delivery tube, it is collected within the gas syringe. Okay, this gas plunger is going to move backward, and the initial and the final gas volumes, they are looked into, and you are going to take out the change in the amount of product which is produced divided by the change in time. And how are you going to measure or record time? By using the stopwatch or a timer. The volume of the gas which is produced or the product which is produced lies on the y-axis. Always the tell me and the time is going to be lying on the x-axis. Okay, tell me where do the dependent and the independent variables lie? Yes, Zoya.
Independent variable is on x-axis and the dependent is on y-axis.
Yes, dependent variable always lies on the on the y-axis, and your independent variable always lies on the x-axis. Okay, so whatever you are changing lies on the x-axis. Whatever impact this has on the onto any other factor lies on the y-axis. How do I remember it usually? And I ask my students to go through this one. D comes here. So the dependent variable lies on the y-axis and the independent variable lies on the x-axis. Okay. Then you see that as the time progresses, the volume of the gas which is produced is marked by this curve. Okay. So when you're looking and investigating the rate of reactions by looking into this curve or this graph, for instance, you are able to see, let me just zoom it in. Okay. All right. So when you look into this particularly, you will see that actually the rate of reaction varies with the passage of time. As the time is increasing, the rate of reaction is also changing. Why is the rate of reaction changing? Because the volume of the gas which is produced, it is not constantly the same at each point, okay, or each time interval, okay. So in this case scenario, how do we find out what is the rate at each point? We're going to find out the gradient, okay? And the gradient of the curve is basically delta y upon delta x. Change in y upon change in x. So change in y here is going to be the volume of the gas which is formed divided by the time taken. So at first you see it is very steep curve, okay? The gradient is very steep. As the reaction proceeds, the steepness tends to decrease. And again, it furthermore decreases. And then when you take out a tangent here, and then it is going to completely plateau off, or it is going to level off at this point in time. This basically suggests that at first, what is happening? Why is the rate very fast? Why is the initial rate quite fast? Can someone tell me? As compared to when the reaction progresses. Yes, Ryan.
Maybe because at the beginning of the reaction, there's more particles that are going to collide with each other, but like the part where the reaction is slowing down, maybe most of the reactants are already formed into products.
Yes, as in the first stage, you can say that the initial rate tends to be greater as compared to the subsequent rates because of greater reactant particles. Okay, very good. So as a result, which is why we see that the initial rate is the gradient of the curve initially is very steep, which means that the rate of reaction is very it's greater as compared towards fast as compared to the subsequent rates. All right, as it gets less and less steep, the tangent is getting less and less steep. This means that the radiant rate of the reaction also decreases, because now the reactants, they are being used up. Okay, as soon as you see that this is going to plateau off, this means that here the reactants, they are now used up, or the limiting reactant is completely used up. Okay, or it is consumed, which is why the reaction has now stopped, which means that the rate is going to be 0. Okay, in the next one, you see the in for this one, let me just zoom the other one in now. This is another method of looking into the rate of reaction, or investigating the rate of reaction. How? We see that in the you're going to add in the reactants, and those reactants, they are added into the conical flask. For instance, marble chips, they are added into they are placed within the conical flask, and as soon as the hydrochloric acid is added, the content of the reaction mixture and the along with the conical flask is first measured using the electric balance. Okay, and then as soon as the reaction progresses, the final mass, when this mass is going to stay constant, then it is again recorded. A cotton wool is placed at the mouth of the conical flask. Why? To for any of the reactant content to leave the reaction vessel. So to prevent any of the contents of the mixture leaving the reaction vessel, a cotton wool is plugged into this mouth of the container. Okay, so but this placing this cotton wool does allow any of the gaseous molecules or the gases which are produced to escape. Okay, so this does allow any of the gaseous particles to escape through this conical flask. As a result, the whole or the complete mass is going to decrease as a result. Okay, so we see that the mass of the flask tends to decrease, which as the time progresses, this tells you that that as the reaction progresses, carbon dioxide gas which is produced is now lost, which is why the mass is going to decrease with the passage of time. So the reaction at first is going to be greater because of the steepness of curve that you see, and as the reaction progresses, it gets less and less steep, and then it is going to completely plateau off, representing that the reaction has now completely stopped. Okay, do we have any questions by far?
No.
Okay, all clear? Yes, Zoya?
Miss, I wanted to ask for the graph of concentration. If we increase the concentration of any reactant, so the end product, will it be more, or like it will just form quickly?
You're asking that whether the rate of the reaction is going to increase, or whether the whole complete volume of the product is also going to increase.
Yeah, I'm asking whether the volume of the product will increase.
Okay, so increasing the concentration increases the rate of the reaction. Okay, but for instance, if I say that you have product A and you have product B, okay, so which means that I'm saying that increasing the concentration would also would increase the rate of reaction, which means that it is going to affect the steepness of the curve. Okay, so if I say that you have two different reactants, one is A and B, okay, and the product which is formed is C. So I say that both of them, they are 10 and 10, and this is 0 at first. All right, but in the next in the next place, I say that this is going to become 20, and the other one still remains 10. Okay, as I am changing the amount of one particular reactant, and this would also increase the rate, or this would also increase the amount of the product. Are you getting my point?
Yes.
All right. So increasing the concentration increases the steepness of the curve. You have to look into the questions. When we're going to look into the past year questions, I will tell you how we're going to decode the questions. Okay. So don't worry.
Miss,
Yes.
so at the end, like, the end time of the reaction, for example, of product C. So this end time of the reaction, will it be the same for one that has less concentration?
No. The amount of product which is formed in a particular period of time, are you saying that the amount of product which will be formed with less concentration, is it going to change or not?
Yeah, like, is the end time on the graph going to differ for both the concentrations?
Come again?
Like, is the end time of the graph,
Hmm.
where the reaction stops,
Hmm.
is that time different for both of the reactions, or is it the same?
Okay. Look, there are two different case scenarios. Now, you can see here, for instance, I say that this is your curve. Okay. This is your curve. And this much is the amount of the gas which is produced. Okay. Let's say this is 30. All right. And this is the time period which is taken. Okay. For the next same amount of, for instance, if you look into this particular reaction, I say that the mass of magnesium does not change, but I'm increasing the concentration or supposedly decreasing the concentration of the hydrochloric acid. All right. So this means that the rate of reaction is going to decrease, which would mean that the curve is going to get less steep. Okay. And this plateau will be achieved later on. All right. So if you can look into this as in this case like that, the plateau phase will be achieved later on. Okay, which means that the time taken to for the same amount of product will be greater. Okay, the for the complete reaction to take place, and to achieve the same volume of the gas, greater time will be required if you're using less concentration. Okay, are you getting my point?
Yes.
Okay. We'll look into questions so that past year questions so that it is going to develop much more conceptual clarity. I've got your point, basically what you're trying to ask. So this is a bit of the thing, but however, when we're going to look into actual questions, past year questions, then only you will get much conceptual clarity, because that is again the ultimate thing. Okay. So moving further, interpreting the rate graphs, we have talked about this, that steeper the slope, the faster the rate of reaction is going to be. The reaction slows as the reactants they are going to deplete. And this is determined by the tangent of the curve, that is your gradient. This gets less steep, which determines that or depicts that the rate of reaction is actually slowing down because of the reactants depleting, okay, or being used up or being consumed. Okay. You can also look into the collision and also the basically your exam questions, they refer to the collision theory. Whenever you are asked to describe a particular factor, you have to look into the particle collision theory and you have to describe or define it in terms of particle collision theory. So usually the questions the examiner is going to give you, it is going to be at least 2 to 3 marks, or maximum 4 marks can come up to. So this means that you have to define the or describe the rate of reaction. How is it being influenced in terms of the particle collision theory? You are going to say that greater number of particles will have more frequent collisions. As a result, the rate of reaction tends to increase. Okay. Activation energy, we've discussed it, that it is the minimum amount of energy which is required by the reactants, and the catalysts, they tend to lower down the activation energy, thereby increasing the rate of reaction. Okay. Okay. Any further questions by far? All right. So I will be ending the session till here. do everybody please write present in the chat box so that I may know that you guys who was present in today's session. Okay. Thank you. Take care. Allah Hafiz. Bye bye.
Allah Hafiz, bye.
Allah Hafiz. Bye.
Last is
Allah Hafiz.